I'm Magne Jørgensen from Simula in Norway, also working at University of Oslo. And hopefully it will not be noisy when I talk because I'm in a hotel lobby in Sydney. This paper and my presentation is about how we measure deviations from what we predict. And in the case of in software development, we might want to estimate how much effort we need to complete a project or whatever we do, or the cost or something else. And as it turned out, the way we do that is not optimal. And that is what I will focus on in my presentation. We don't have a precise understanding of what we estimate, and we don't have measures that reward the most unbiased estimates or predictions. By the way, there's difference here between accuracy and bias, which is important. This is about bias. That is how much we tend to, for example, underestimate the cost of the effort. And while accuracy does not say anything about the direction, whether we under or overestimate, bias has a focus on the tendency to be over-optimistic or over-pessimistic or something like that. I have included a quote by a professor in statistics called Magne. He says, and that is the starting point for what I did here, the common practice of requesting some point forecast and then evaluating the forecast by using some set of scoring functions is not a meaningful endeavor. Magne has looked at this for accuracy measures, and of course he is much more skilled in statistics and mathematics than I am, but still he and no one else seems to have looked into the problem we have to evaluate bias when we predict something. And this is that we need to be precise about what we mean by a forecast or an estimate, and we need to have a scoring function, an evaluation measure that rewards the type of estimates that we would like to reward. Okay. Yeah. So why do I look into this? Well, we need estimates of effort or cost to for example, as input in bidding or budgeting or planning or other purposes. So no one will start a project without knowing whether this is going to be cost-benefit efficient, for example. Yeah, and when we have our estimates, we want to evaluate them as well, because we want to know, do we tend to, as is the case in software development, is there a tendency to be over-optimistic? And that is useful input to improve. And we also might know who are the best estimators. And we want to reward and those who are best. And we also we know that if an estimator knows that he or she will be evaluated, then it's more likely that they will be realistic. They spend more effort on trying to be realistic. So there are many reasons why we need an estimate and why we want to evaluate its bias and accuracy. But this is a focus on the bias. So, as I mentioned, there are many challenges related to the proper evaluation of predictions or estimates. There's only two of them that I have looked into here. That is related to what we mean by an estimate and what are measures that reward the best estimates. So my surprise was that in spite of that we have been estimating a lot of things for decades or centuries, the type of measure that we use are actually not having the properties necessarily that we like them to have. And this hasn't been addressed neither in research guidelines or in industry. Well, it might not be that important because if the bias is large, well, if you do some small mistakes on how we evaluate them, it's not that bad. But as I will show this, the way we evaluate is not only a little bad, it's actually very bad. So the roots of the problem, we have to start with the understanding or the acknowledgement that at the time we estimate the effort for software development, there are not only one possible outcome, there are many. And the distribution on the right-hand side here shows that this distribution of possible outcomes is a probabilistic or stochastic view on the use of effort, which is a realistic one. And we can see here on the left-hand side, if nothing goes wrong and we have the wind in our back, I mean, everything goes smoothly, then that is the most optimistic use of effort. Then we use maybe around 80 weeks or hours or whatever the unit is. Most likely we'll use around 100. And we might also think that looking back that around 50% of the times we will use less and more than 20. If you want some estimate that we are pretty sure that will not be exceeded, then we might need a so-called P85 estimate, 85% likely not to be exceeded. And worst case is, well, can be as bad as you want. As we know from some projects, it can take an immense amount of effort. So there are, and the typical property here is that it's not symmetric, this distribution, it's right skewed. So that's the first step and the first root of the problem. We need to understand that the outcome is a stochastic variable. What we try to estimate is stochastic. And that means that when we say that my estimate is, and we say a number without pointing out where on this distribution are we trying to estimate? Are we trying to estimate the most likely effort, the most optimistic, the median, the mean, the expected value of this distribution, or something else? So clearly, this is, by the way, a pretty realistic distribution. If we just say a number and say my estimate is, without pointing out which element on this distribution are we trying to estimate, that is very poor communication. It's like in the picture, and this developer perhaps on the left-hand side is asked about his estimate, and he or she responds, I estimate this to take around 700 hours. He might think about this is the best case if nothing goes wrong, most optimistic, while the manager perhaps you ask him will think that, well, this is something I can use as my budgeted effort, the planned effort maybe. And this is of course leading to that maybe the developer's estimate is perfect, is exactly the right one, given that nothing goes wrong. But usually not everything goes smoothly and ends up with something else. So the manager will believe that the estimate was wrong. But in reality, not the estimate, but rather the communication went wrong. So, and that is the main part of the paper. Without communicating what we mean with an estimate, we cannot meaningfully evaluate its accuracy or bias. And so that might also be the reason why it hasn't had a focus earlier, because the first step hasn't been there. So then it means that we cannot really say much about the properties of the measures that we use. So first step is that we need to know what we estimate, mean, median, most likely, mode, or something else of this distribution. Yeah. So first, at that stage, we can evaluate to what extent our measures are proper, that they actually give the best score for the best estimates, that they, if you are having unbiased estimates of the mean effort or the median effort or the most likely effort, it rewards those who are actually median or mean or median or mode unbiased. Okay, so a main part of the paper looks at one commonly used measure, which is the following one. Act is the actual effort and est is the estimated effort. So this is the relative bias of the estimates. And as you can see here, if the actual effort is systematically higher than estimated, we will have a positive value. while if we have as much over as below the estimated, we will have a zero bias. And it's the mean value of all the deviations or the relative deviations here. So if we again look at distribution, which in this case has a mode, the top point of distribution of 162, the median, which is 50% likely to be exceeded, of 209, and a mean of 236. Of course, we don't always, we know that we need to estimate these values, but that's not the main, that's not destroying the message here. And yeah, this is distribution of what we think are the outcomes, the possible distribution of possible outcomes of software development project or task or whatever it is. So let's say that we as a developer know that we will be evaluated using the measure that I have on this slide. Where on the distribution should you put your estimate? Should you try to estimate the mode, the median, or the mean of this distribution? That is the problem. If you want to score optimally on this measure, what a type of estimate should you give? And that turns out to be surprisingly difficult, because neither the mean, by the way, the mean of this distribution is what typically estimation models will give you. So if you have a linear regression-based estimation model, or use the so-called PERT formula, which is common in the industry, it's the mean effort that they try to estimate. And as you can see in the paper, if you have a perfect estimate of the mean of the outcome distribution, you will expect that this bias measure says that you have a strong tendency towards underestimating the effort. So perfect estimates of the mean will actually not give you a zero bias score, but will give you a very bad one. And not as bad, but also bad. The median will give also expected underrun of 40%, and the mode will tell those who use this measure that you have been over optimistic. While in either of these cases, assuming that you have perfect estimates, you were actually unbiased, but the measure will tell you that you were biased. So this clearly points out that this measure is not being optimized, having zero bias for any commonly used interpretations of an estimate. So, and the paper derives what would be the optimal estimate to achieve a zero bias. And well, that's a pretty mathematical proof, but it's not a complex one. But in reality, you have to give a value that is between the median and the mode. 184, yeah. But of course, that is not possible for any estimator to know that value is the one you should give. So this is mainly to illustrate that we have no clue what we would give, given that we are evaluated by this measure. We'll not know what is the optimal estimate to give to appear unbiased. Yeah, and this property of the above measure of bias has not been pointed out anywhere. Well, it's used in many disciplines, not only in software development. Still, it's very surprising that I haven't found anywhere else that has pointed out this unfortunate property that is not optimized by any common understanding of an estimate. So what are the consequences? Well, you punish accurate estimates, or unbiased estimates is more correct to say, and biased estimates might be rewarded. So if a company use an estimation method that aims at giving the mean value, mean effort as their estimates, and they actually score a zero bias using this measure. Everyone will believe that, well, they have done a really good job at estimating. But in reality, they have been strongly underestimated the mean effort. So in order to appear good here, you cannot estimate the mean, but has to estimate something much lower, and you're rewarded for underestimating the mean effort, which is, of course, bad. So you're punishing those who have accurate estimates, and you are rewarding, potentially at least, those with biased estimates. So, and it's even worse in this case, since it rewards underestimating the mean effort. Yeah, and it also has the consequence that we have no way, no simple way at least, to give estimates that gives a score that is perfect, a zero bias score with this measure. Yeah, in short, we should stop using the above measure to evaluate estimation bias. So things like cost overrun in projects, we should use other measures. And that is the message. So what to do? There are actually measures that are meaningful. And the first one is actually a very simple change of the one I showed earlier. If we, instead of dividing by the actual effort, divide by the estimated effort, then it's optimized by the mean of the distribution. So then we can use the mean outcome, estimates of the mean outcome as our estimates. And if we have perfect estimates of that, we will get a zero bias on this measure. So simply switching the what we divide by from actual to estimated effort helps, or not only helps, that gives a proper measure of the bias. And we can also use, instead of relative measures, the absolute deviation, not having the relative that has other negative properties, like it's not relative, it's not scale free. Yeah. So if you want to estimate the mean effort, 50% likely to be exceeded effort, then there are other measures. We can still use we can then use the median, not the mean, median of the absolute deviation. We can use both the ratio of actual estimate divided by the actual or by the estimated, or we can use the log of them. So, but it's the important difference to the above is, of course, that we don't use the average, the 1 divided by n, but we use the median of these values. These measures give an expected bias of 0 for perfect estimates of the median effort, which is what we would like. Interestingly, the most likely effort, which, by the way, I think is pretty common, it's hard to document, is the estimate that is typically given by software developers. There are no really good measure. One message that which I planned to have in the beginning, but I can tell you now, is that when I've conducted some studies of what do the companies and software developers give as their estimates. Do they give the mean, the median, or the most likely, or the most optimistic as their estimates? So I have had a number of studies asking them in companies all around the world, actually. And it turns out that it's not nice, but it's a large spread of what they mean by an estimate. So I would say about 1/3 of the companies and the people, they interpret their estimates as some sort of best case estimates. And 1/3 as well, around interpret their estimates as the most likely. And then the remaining are spread on the median and the mean and something else. So even within the same company, there's a confusion about what they mean. So they have a very different opinion of what an estimate is, and they don't communicate it. But so that again is the first step, and that is what I point out here. So the first step is to have a precise interpretation, understanding of what we estimate and communicate it. Then we can find a measure that is proper in the sense that it rewards unbiased estimates. So that is my message, and the last slide as well. So I'm, as always, open for questions, or you can read my paper on this, of course.